So, hello everyone. So, thank you for coming to the Cosmic Ray session. So, I think not so many users use FITS for Cosmic Ray research. So, because most users use for like shielding or medical physics. So, I'm happy that they're still you're interested in Cosmic Ray research using FITS. So here are recent versions. We implement cosmic ray source function. So in this lecture, I would like to teach how to use cosmic ray source mode in FITS. First, I would like to explain about the cosmic ray environment. So I think most of you know there are three types of cosmic rays. One is the GCR, galactic cosmic ray, and solar energetic particle, SEP, so-called SEP, and trapped particles. So galactic cosmic ray exists everywhere in space and atmosphere, and its temporary variation is gradually changed by solar activity cycle, generally 11-year cycle. And the spectrum is very hard, and the highest energy of the cosmic rays up to 10 to the 20 electron volt. So extremely high energy cosmic ray exist, come from the galaxy. So it is generally created by the supernova explosion, but still the origin of the galactic cosmic ray is under discussion. So on the other hand, solar energy particle exist in space and seldom in atmosphere because the energy of solar energy particle is not so high compared to the galactic cosmic ray. So most of them are bended by the magnetosphere, geomagnetic field of the Earth. And its temporal variation is very impulsively changed during the solar particle event. So generally, there is no SEP around the Earth, but once extremely large solar flare occurs, so many solar energy particles come to the Earth, and some of them pass through the magnetic field and also atmosphere, and sometimes detected by ground-based neutron monitor. But it's quite rare, so only once per a few years or even less recently. And the spectrum is rather soft compared with GCR, as I said before, so that's why it cannot incident to the Earth's atmosphere. And the energy is up to a few GeV, but this is quite extremely huge event case, and in most case, 100 MeV or a little bit more than 100 MeV is the maximum. And last one, trapped particles, they exist only in the magnetosphere around here. And its temporary variation is gradually changed by the solar activity cycle in the same as the galactic cosmic rays. And the spectrum is also soft, is similar to SEP, and up to several hundred MeV. So, and all of these three types of cosmic rays can be considered in FITS as the source particles. Galactic cosmic rays we can consider outside magnetosphere, in the magnetosphere, atmosphere. Solar energy particle we can consider only outside magnetosphere and inside magnetosphere. So we don't have any mode to generate solar energy particle in the atmosphere. And the trapped proton, so This exists only in the magnetic field, so we can generate the cosmic trapped particle spectrum only in the magnetosphere. And in FITS, we use these models to generate the cosmic rays. For GCR case, in space and the low Earth orbit, LEO indicate low Earth orbit. That means in the magnetosphere, but the orbit is rather close to the Earth. So it's International Space Station is on this orbit. And in space and low Earth orbit, we use DLR model. And in the atmosphere, we use PALMA and XPAX, which is developed by myself. And in this case, we can consider altitude, geographical, and angular dependence of GCR flux can be considered. For the SEP case, solar energy particles in space is calculated by Tilka model. And in the atmosphere and the low Earth orbit is, as I said before, it's not applicable. And the trapped proton, we can consider only in low Earth orbit, in the magnetosphere, using the AP8 model. And here is the reference of the model. Okay, so this is a very rough explanation of the cosmic ray environment, and I would like to go to the exercise. And in the same as the other exercise, when you finish the exercise, please push the yes button. And if you have any questions, you can raise your hand, or maybe so we don't have not so many participants, so it's also okay to directly turn on the mic and share your questions with other participants. That may helpful for other participants, so don't hesitate to ask directly. Or also you can use chat as the same as other lectures. So here, Shigeo-san and Matsuya-san is in this room, so they will answer your questions immediately. Okay, so let's do the exercise. So first, let's run cosmicray.imp. Simply run it and check 3 EPS files. So one for the track xz.eps that shows the cosmic ray flux, and the track en and hyphen underbar rec.eps shows the energy spectrum, and the cross.eps shows the angular distribution of cosmic ray crossing this surface. And the geometry is concentric shells, spherical shells with radius of 100 centimeter, 110 centimeter, and 200 centimeter. So this shell roughly represents the spacecraft. So actual spacecraft is more like complicated, but for like a lecture purpose, I don't make you confused with the complicated geometry. So simply spherical shells are used for the spacecraft. Okay, so let's run cosmicray.imp and check the EPS file. And I already put the folder location to chat. So if you cannot find the input file, please check chat and go to the Cosmic Ray folder in the advanced lecture folder. Okay, so let's do this exercise. So when you finish the exercise, please press yes button. So it's just one fit. Just running fits. So if you can find the folder, so it's not so difficult. Okay, so I will do it on my screen too. So here is the input, and simply I run it. Then I got several EPS files, leg, track, XZ, XY, and cross. So in the cross.eps file, so this is downward directions. -1 is downward direction. +1 is upward directions. And the cosmic ray source is generally generate source in isotropic way. So the same number of particles goes from down to up and up to down, or sometimes horizontal. And this picture is actually rotated by 90 degrees. So during the option lecture, Oga-san gave on Tuesday, someone asked that how to rotate the EPS file, and this is the answer. So you can translate by 90 degrees and change the axis to this way. So without this command, fits draws a graph by Z and X. But here we would like to see that, imagine that this is downward, this is upward. So I rotate it, the figure. Okay, so next, I would like to explain about the recommended parameter setting for generating cosmic rays. So cosmic ray is quite like a special simulation. So you need to turn on some parameters. And the first one is the event generator model is generally recommended to use. And IRQMD is a QMD model version. And IRQMD 2, 1 indicates a version 2. And it's cost computational time, but the more accurate. And there's a lots of heavy ion, particularly in GCR, galactic cosmic ray. So I recommend to use JQMD version 2 for your cosmic ray simulations. And NEGS equal to 2. And usually people use -1 is the original, fits original photon transport only, or +1 is the easiest mode. But the 2 is the high energy easiest mode. So the highest energy of photon, electron, and positron transported when NEGS is set to 1 is 1 GB. But in the cosmic ray simulation, sometimes higher energy electrons are generated. So we recommend to set higher Gmax, 10 to the 8. So, but if you set to NEGS equal to 2, then these maximum energy of photon, electron, positrons are automatically set to 10 to the 8. So 100 TeV, so extremely high energy. 100 GeV, sorry. Yeah, no, TeV is okay. Yeah, 10 to the 3 is 1 GeV, so 10 to the 6 is 1 TeV, so 10 to the 8 is 100 TeV. And MDV Atmer is the maximum database size of Atmer. So when you transport cosmic ray, so many varieties of secondary particles are generated. So sometimes the maximum, this parameter suggests the maximum projectile and target combination of stopping power database. And every time a new combination of projectile and target is generated in FITS, it's used a database. So usually 500 combination is sufficient, but in the case of cosmic ray transport simulation, sometimes 500 is not sufficient. So we increase the default value to 3000. And the last one is also very important for cosmic ray simulation. So IMeV per U is a parameter whether tally particle energy is MeV or MeV per nucleon. And in the case of cosmic ray transport simulation, so people usually estimate like a plot, like a helium flux, ion flux in the unit of MeV per U. So we recommend to use this number. And also this parameter is indispensable when you want to calculate the dose equivalent, as I explain later. So okay, so I got a question, why use of 3000? Actually, this is arbitrary. So generally 3000 is enough, but sometimes you will see that the MDV Atmer is not enough in the console. But it's just decrease the computational, increase the computational time, but the result will be the same. So you don't have to stop and rerun the simulation. So basically, you can continue to, even you see the warning, you can continue the simulation. Okay. Any other questions? Okay, so next I would like to talk about how to set up source section. And the cosmic ray source, so the various ions exist in space, but only one projectile can be specified in one multi-source. So each multi-source is recommended to be defined in an include file, except for project parameter. So in this cosmicray.imp, in the source section is quite short. Only parameter C. This is maybe I have to explain this one first. So this is a source condition, cosmic ray generation condition except for the projectile. Generally, cosmic ray source is recommended to generate in the sphere. Spherical source is recommended to use because it's come from the every directions. And S-type Q9 case, R1 and R2 is a radius of sphere, and the source sucks. So it's not so good explanation, but sometimes you want to set up the inner radius and the outer radius, but generally inner and outer radius is the same, so you can make a spherical source. So, and the radius is defined by C1 parameter. So in this case, 200. So 200 is the size of this one. Then direction should be set to isop, the isotropic source. And E-type equal to 25 indicates a cosmic ray source. So 25 and 26 is a cosmic ray source, but 25 is actual number of cosmic rays are generated in each beam. So if the flux is small for a certain energy beam, the number of particles generated from the beam is also small. But here set to E-type 26, equal number of particles are generated, and the particle weight is controlled to reproduce the cosmic ray spectrum. So basically, you can use 25 for the source. It's more easier, and you don't have to care about many things. So I recommend to use 25. Except when you want to highlight the high energy contributions. And ICE EMV, this is I cosmic ray environment parameters, and this defines the type of cosmic rays. And 0 is a free space galactic cosmic ray. Free space means outside magnetosphere, so in real space. And the positive number is a terrestrial ZCR, so you can reproduce atmospheric cosmic ray, terrestrial cosmic ray, using the positive number. And the negative, if you set to negative number, you can estimate the free space SEP. And also, trapped proton is also the negative number, but I forgot exact number. You can check it by manual. And the very important things of cosmic ray source in comparison to the other source is the absolute value of the cosmic ray is also determined in the same as Ri source. So if you set the thought factor parameter to the surface of the source, then you can directly estimate the tally quantity per second instead of per source. So it's the same as Ri source case. In the Ri source cases also, you can directly define the Becquerel, then your tally result is per second. And also cosmic ray sources case is also the same. So you can directly get the per second data. So it's very convenient. So you don't have to consider about the normalization by yourself. And to do that, you have to set thought parameter to pi r square, and r is the radius of the sphere, and also source parameter should be 1, even you define several multi-sources. Okay, so I got the question. Is it possible to simulate the real altitude of the atmosphere, or this will CPU consuming? The answer is yes. So you can reproduce a certain, like a cosmic ray environment at the 12-kilometer altitude, like a flight altitude. And it's just change the spectrum. So CPU time is the same, basically. It's nothing changed. Basically, simply change the energy spectrum is changed, adjusted to a certain altitude, but it's not time consuming. So you don't have to transport like you don't have to reproduce the air shower simulation by yourself to reproduce cosmic ray at a certain condition. So that part has been done already by me, and I make a model for every location in the world. So basically, you don't have to run air shower simulation by yourself. Simply, you can generate a certain cosmic ray conditions, and if you put like an aircraft in the spherical target, so you can estimate the influence of the aircraft shielding if you want to do such simulation. So you don't have to start from the top of the atmosphere. Okay? Okay. So exercise atmospheric composition can be changed. Basically, atmospheric composition is not so much altitude dependent, but of course, density is very much altitude dependent. And that part is you have to reproduce by yourself. So check the density at the, yeah, yeah, at a certain altitude and input the density by yourself. Okay, so let's do the exercise one. So add helium-4 and iron-56 to the source particles. So for this exercise, you can understand why I use include file for the source, because these parts are the same for every multi-source. Only difference is a project parameter. So you can simply include file again and write the projectile, and include file again and write the projectile. Okay, so let's do this exercise. When you finish, please press yes button. Okay, so I will show the answer in my screen. So first, copy and paste, and the project is set to 4 helium. And second, and copy and paste again, and the project is set to 59 ion. And save, run, fits. So now I see protons, alpha, and the ion. But generally, the cosmic ray is dominated by protons. So proton flux is, as far as I remember, 90%. Alpha particle is roughly 9%. And other ions are only 1%. So it's quite rare to generate ion with this setting. So it's slightly different from this picture, but anyway, you can get similar data. So next exercise is generate equal number of particles for protons, helium, and ions. And to do that, negative thought fact parameter indicates that equal number of sources are sampled from each multi-source, and their intensity are adjusted by weight. So let's add minus in front of pi and run fits and check the difference of this picture. Okay, so let's do this exercise. So I think this is rather easy task. simply add minus here and save, run it. So we can get the equal number of protons, alpha particles, and ion. But if you see the proton statistical uncertainty, it's become worse because number of generated protons are reduced due to these particles. Next, let's change the solar activity to the solar maximum. So currently, so let's open source.inf. And in the source.inf, solar mode parameter is the solar modulation index. So-called W index. So W index can be directly specified solar mode parameter or determined from dates specified by IC year, IC month, and IC day. So which has a database of solar modulation, daily database of solar modulation from 1950, I think, as far as I remember. So quite long time ago. Every day, the cosmic ray intensity is already evaluated. So you can specify the date of your interest, which automatically reproduce the situation. But here, we can directly specify the solar modulation, solar activity index. And now, 0 is the solar minimum case, and the maximum case is around 150. So that W index is similar to sunspot number, but not exactly the same. But so if you set, so please change the solar mode parameter to 150 and check the difference of the spectrum. Okay, so I got a question. So is it possible to change the solar mode parameter database or in terms of manually? Of course, you can change solar modulation parameter as you want, but like a date and the solar modulation parameter database, you cannot change it because it's already evaluated. So if you want to specify a certain solar modulation index, so you can directly input the number without specifying the date of your interest. Okay. Okay. So I will show the answer here. So it's so first you have to open source.inp and change this number to 150 and save. And don't run this file itself. If you run this file, you will get some error because this is only a certain part of the source. So the file you need to run is cosmicray.inp itself. Then you will see the decrease of low energy flux. So if you compare with this is a solar minimum case, and if you change to 150, it's low energy flux decrease very much because solar activity and the GCR flux are uncorrelated due to the solar wind. So strong solar wind prevent the galactic cosmic ray from the entering to the heliosphere. So push back the GCR out of the heliosphere. So that's why the cosmic ray flux and the solar activities are uncorrelated. How is W index related to sunspot number? It's rather difficult to answer. So actually, W index itself has no relationship with sunspot number. So the way to evaluate W index, we use a count rate of ground-based neutron monitor. And from the neutron monitor count rate, we estimate W index. But the absolute value of W index is adjusted to be resemble similar to the sunspot number. So that's why these two quantities looks like correlated. But the evaluation method is completely different. So sunspot number is simply observe the sun, but the W indexes come from the cosmic ray observed cosmic ray intensity. So it's more closely related to the actual cosmic ray intensity. This is because activity of 2 or 3 months before sun is related to the correlate with the current cosmic ray intensity. Because cosmic rays come to the Earth rather fast compared to the solar wind. So when sun explodes the solar wind, it takes several months to go to the scatter to the heliosphere. On the other hand, cosmic rays coming to the Earth just maybe within months, but not so immediately. It takes roughly a month to get into the Earth from the out of the heliosphere. So, but anyway, there's a time difference between the solar activity and current cosmic ray intensity. So, W index is more closely evaluated from the current cosmic ray intensity of certain date. So, better index to express the cosmic ray intensity, definitely. So sunspot is number is just a rough representation of the cosmic ray intensity. Okay, so next is consider rigidity cutoff by magnetosphere up to 10 gigavolt. So usually the rigidity cutoff is expressed in the unit of gigavolt. So this means the particle with rigidity below 10 gigavolt cannot reach to a certain location. So low rigidity cosmic ray cannot penetrate the magnetosphere, and the cutoff rigidity can be specified by rigid parameter in GeV. And maybe some of you never heard the term of rigidity. So rigidity is the effect of magnetic field on the motion of charged particle. So if the particle has high energy, so it has high rigidity because it's so hard to bend the particle by the magnet. But if your particle has higher charge, then it's easier to bend. But a particle is also heavy case. It's hard to bend by magnet. So in the like a particle transport simulation on the Earth, like a fit simulation, rigidity is not so important. So particle energies or momentum is more important to decide the characteristic of radiations. But if you go to the space and in the vacuum area, so everything is controlled by rigidity. So proton with rigidity 1 gigavolt and ion with rigidity with 1 gigavolt move exactly same the trajectory. So in the space, particularly like a high altitude, like a geomagnetic research area, people always talk the radiation in always in rigidity. So that's why we use this index for using the cutoff rigidity here. So anyway, so let's change the rigid parameter in cosmic ray, source.imp and the save and run cosmic ray.imp and check the difference of the spectrum. So if you change the rigid to 10 and save and run run cosmicray.inf, then we can see this picture. So 10 gigavolt rigidity is not always the same as a function of energy. So proton 10 gigavolt is almost equal to the proton with 10 gigavolt rigidity is almost equal to the 10 GeV protons. But for like alpha or iron ions, it's roughly 4 GeV per nucleon. And usually we use vertical cutoff rigidity as the index for expressing the strength of magnetosphere. And at the polar region, vertical cutoff rigidity is 0. That means almost very low energy cosmic ray can incident to at the polar region. But at the equator region, vertical cutoff rigidity is 16 gigavolt. So in the case of protons, proton with energy below 16 GeV cannot incident to the atmosphere at the equator region. So only very high energy protons can incident to the atmosphere. Okay, so next let's try to reproduce the cosmic ray environment at the altitude of 12 kilometers above New York. So to reproduce a terrestrial cosmic ray, you have to set ICM parameter to 1 in the atmosphere mode. And in this case, rigid parameter is not necessary to define, and add GLAT and ZLong parameter for specifying the geomagnetic latitude and longitude in degree, and add alt parameter for specifying the altitude in kilometer. So, and New York is located at the latitude of 41 north and longitude with minus 74 in the west coordinate. So please set this way, change the source.1.inf in this way, and save and run cosmicray.inf and check the energy spectrum. Okay, so I would like to show the answer. In source, comment out the rigid parameter and the ICM equal to 1 for to make the terrestrial mode. And add these parameters. Sorry. And save and run fits. Then I got this distribution. And yeah, I got the question. So can we calculate the cosmic radiation exposure of aircrew using Fitts code? So as Matsuya-san answered, it's yes. But if you want to simply calculate the dose of air crews, you don't have to use Fitts. You can directly calculate the number using XPACS. So I think many of you knows about XPACS, but I would like to introduce here. So this website is also under the Fitts website, XPACS page. And if you go to the download page, you can direct download the XPACS. And in this software, you can easily calculate the dose by specifying the condition. So for example, if you set to like altitude of 12 kilometer and latitude and longitude and year, month and date of your interest, and set like a pilot location, then the effective dose is directly comes here. So if you simply want to calculate the aircrew dose for certain condition, you don't have to use Fitts. So of course you can calculate using Fitts, but it's much easier to use XPACS. But for example, if you want to consider like aircraft shielding effect by yourself, then you have to reproduce the source of a certain place in the Earth and construct aircraft geometry by yourself and run Fitts and estimate the dose inside the aircraft. That's what you need to do. So it depends on the purpose. You can use either XPACS or Fitts itself for calculating the dose of aircrews. Okay, so next, if you check the angular distribution, you can see this kind of distribution. So downward, upward. So cosmic ray environment in the atmosphere is not isotropic, and this anisotropy can be reproduced by the Palma model that I developed. So protons are rather like a downward directionality proton has, but some low energy proton go upward. So it's not completely downward spectrum, downward flux. For the iron, so there's almost no secondary iron ions. So all irons are going to the downward direction. Except for here. So this is because due to the round shape of atmosphere. So like if the Earth is something round shape and altitude 12 kilometers is here, so some ions going to these directions, just passing through the Earth. So if you consider such contribution, some ions are going to upward, but most ions are going to the downward direction. So let's move to the next exercise. So change the source to more abundant cosmic ray in the atmosphere. So ion flux are very small in the atmosphere, except for very high altitude. So change project parameter in source and the part in tallies to secondary cosmic rays, neutron, muon, plus minus, electron, positron, and photons. So please change these parameter, these lines. So input source is the same, but the project should be neutron, project should be muon plus, project should be muon minus, project should be electron, project should be positron, project should be photon. So you have to set up 6 multi sources and change the part parameter to these 6 particles. Okay, so let's do this exercise. Okay, so I would like to show the answer here. So change neutron muon plus muon minus, copy and paste again, and electron positron and photon. And change the tally particles to neutron, muon plus, muon minus, electron, positron, photon. And here, okay, and save, run bits. Then I can see many variety of particles here. And also the angular distribution is very complicated. Neutrons are rather isotropic, but their muons are quite downward directivity. No, muon, this one. This one is muon. Photons also have downward directivity. And so big difference with the angular distribution. Okay, so why we need to define the secondary particles muon plus muon minus in the source section, as these particles are produced from the interaction primarily with the atmosphere. I mean, we can only define. Okay, maybe so. You misunderstand the concept of the cosmic ray source mode in FITS. So in FITS, air shower simulation is not performed. So if you start with the top of the atmosphere, it takes extremely long computational time to get to the a certain location, for example, at the ground level. So I already did this simulation and make a fitting formula to reproduce the spectrum. So if you want to reproduce the cosmic ray environment at a certain point in the atmosphere, you can start with that spectrum. So you don't have to start from the top of the atmosphere. So in FITS, so in this FIT simulation, so we did not perform the atmospheric transport simulation. Only we simulate within this area. So before coming to this area, so if you start from the top of the atmosphere, protons comes and many secondary particles are generated. And at a certain point, neutrons, muons are passing through within this target. But it's extremely time consuming to start from the top of the atmosphere. So these parts are already passed by, and there are only particle fluence are already pre-evaluated particle fluence, including secondary particles, are generated from this point. Okay, so neutrons are And the next question is there any explanation for the isotropic distribution of neutrons? So because neutrons are scattered many times. So originally, when the neutrons are generated, it's quite high energy, but it's scattered so many times. And once neutrons become like a thermalized, so almost he forgot the original directions. So the muon case, it's quite rare that the muon scatters so many times. So it still remember the first time they are born. So they are born to the downward directions and keep going to the downward direction. But the neutrons at the beginning they are produced by downward direction, but they are scattered several times. So original direction is disappeared. So original information on the original direction is disappeared and become isotropic. So if you pick up only high energy neutrons, still they have directivity. And in the Palma model, angular distribution is evaluated as a function of energy. So if you generate only high energy neutron in the pits, neutron has also downward directivity. Okay. Okay. Could we estimate the angular dependence with energy with fits? Yes, you can. Simply, you can define a certain energy range in the source generation. Okay, so for example, the energy is specified by EZ0 and EZ1 or EZ1 and 2. I forgot. Let's try. Maybe 100,000. Then energy. Yeah, so we generate only high energy particles now. Then cross EPS is more like a downward directivity, strong downward directivity. So if you specify a certain energy range, then you can get more, you can get the certain energy angular distribution. But also angular distribution can be directly estimated from XPaths. So if you set up like conditions, so but in the XPaths, you can not get the angular distribution itself. So you can estimate the energy distribution of a certain angle cosmic ray. So here, red line is to upward directions. Yeah, downward direction. Well, downward direction. So it's a little bit complicated, but cosine theta 1 is downward direction in XPaths and -1 is in bits. So this is a downward neutron energy spectrum. And if you set to like 0, this is the same as 3. So this one is like a vertical, not vertical, it's a horizontal neutron flux. So low energy, so all neutron flux are almost isotropic, so there is no angular dependence. But the high energy, there's a huge angular dependence. So you can get this information. But in Xbox, there is no function to plot the flux as a function of cosine theta. So if you want to estimate the angular distribution itself for certain energy cosmic ray, it's better to use FITS. Okay. So this is the answer for exercise 6. Okay, so exercise 7 and I will take a break. So after exercise 7, I will take break. So let's reproduce a cosmic environment at the ground level of New York. So in that case, change ICM parameter from 1 is the ideal atmosphere case to 2, it's a ground level case. So at the ground level, neutrons are scattered from ground. So it's different from the atmospheric atmosphere case. So the good thing of this model is you don't have to specify the altitude to 0 or not always 0. But also like if you want to know the ground level neutron flux at the top of the Mount Fuji, you can specify ICM equal to 2, the ground level model mode, and the altitude is 3.776, the altitude of the Mount Fuji. So then you can estimate the ground level neutron flux at the altitude of 3.776 kilometers. So, but anyway, now let's assume that the sea level of ground. So let's change these two parameters and run fits and check the difference of the flux. Okay, so I think it's a not so difficult task. change the ICM to 2 and altitude set to 0. And round fits. Yeah, I did again. Round fits. So now energy spectrum is like this, and the flux distribution is like this. So the difference between the atmospheric and the ground level mode, atmosphere mode and the ground level mode is low energy neutron flux, and it's albedo, so-called albedo neutron, and it depends on the water density in soil. So you can define the water density. So it is on the sea or on the desert or like conventional, like on the concrete. So you can specify such conditions. And also horizontal muon flux are collected by like ground level experimental data. So that's also high energy muon flux at the horizontal direction also change by change the ICM from 1 to 2. Other flux condition, other flux the same. Doesn't influence by the ground. Okay, so let's take 10 minutes break and let's start the course at 9:45. So 12 minutes later. So in UTC, I think 10, 10:40 at 12:45. Okay, so let's take a break, about 10 minutes. Okay, so let's resume the course. So next, let's calculate the astronaut's dose in free space. So first, change the project to protons, and other ions are ignored for simplicity. And change ICM back to 0 in free space mode, and comment out zlat, zlong, and arch parameter. And activate the last T-track with file equal dose, track underbar file equal track underbar dose dot out. And with this tally, we calculate the effective dose equivalent using the multiplier functions. And for astronauts, generally the dose is evaluated in effect dose equivalent instead of absolute dose, because cosmic ray has high relative biological effectiveness. So we need to consider high RVE of the particles in the dosimetry, astronauts dosimetry. However, conventional effective dose can be used only for the ground level dosimetry. And in space, it's widely used dose equivalent. And in FITS, there is a database of dose equivalent. And that multiplier ID is minus 211. Is their effective dose equivalent. And this number is a conversion from picosievert per second to microsievert per day. And okay, so let's change these and run FITS and check out the track underbar dose dot out file and check these two numbers. Okay, let's do this exercise. Okay, so I think you get similar result like this. And these are the dose equivalent in microsievert per day. So roughly 140 microsievert per day, both inside and outside of the target, because currently everything is void. So next, let's change the calculate astronauts dose inside spacecraft. So change the material of cell 2 to aluminum, and change the max cost from 100,000 to just 1,000 for reducing computational time. And check the dose. Once you run FITS, you please check the track underbar those out. Okay, so I would like to show the answer here. And actually, this is the last exercise. We have two more exercise, but we don't have enough time. So this will be the last exercise, and I would like to show the answer. So first, I have to change the material of cell 2 to aluminum, and the density is minus 2.7. And save, and no, run fits. Ah, I forgot to change the max gas to 1000. Otherwise, simulation took very long time. Then, so now particles interact with this shells, aluminum shells, and many secondaries are generated. And those here, the total dose inside the sphere is higher than that of the outside. So it's a little bit surprising because many neutrons are generated by the aluminum shells. So just a small shieldings makes GCR dose higher. So it's so difficult to shield the galactic cosmic ray. So you have to be very careful to protect the astronauts from the galactic cosmic ray. Like a small amount of material simply increase the dose. But of course, if you consider heavier particles, so situation is slightly different. So it's not always increase this much level, but anyway, a slight shield increase the dose of astronauts. So that must be very important point. Okay, so after this, maybe next exercise is make a lunar surface here and consider the certain limits certain angle cosmic ray, because in the lunar simulation case, all cosmic ray comes from the upward. So you need to set up AG1 and AG2 parameter to limit the direction of incident cosmic ray. And also, you can do the simulation for SEP by changing these parameters. But I think it's not so difficult to simply change the ICM parameter to negative and environment parameter to 1, 2, 3, 4, either 1, 2, 3, 4. So everything is written in the manual. So please check how to make solar energetic particles instead of galactic cosmic ray. And if you simulate the solar energy particle, situation is completely different. So like a small 10 centimeter of aluminum extremely reduce the dose because the energy is so soft, energy spectrum is so soft. Okay, so here is a summary. So I'm sorry that I skip a little bit lectures, but I think most important part I already explained. So I think you can use the cosmic ray source mode and you will feel very useful for this mode. Okay, so no, does that means you double the number of particles? No. You mean normalization is still you don't have to care about the normalization. So what fits do? Yeah, normalized. So what fits do is simply if randomly selects the directions and if the selected direction is prohibit area, simply ignore the source and go to the next history. So simply fits do not produce any particles, but the histories go one next. So uh, yeah, normalize. So you don't have to care about the normalization. Still, if you prohibit certain direction, still normalization works as it is. So any other questions? Sorry that time to start the next session. So maybe you cannot take a break. So, but anyway, we already took a 10 minutes break, so you can continue to take a lecture, I hope. Okay, thank you very much. And so please, if you have still have some questions, please stay in this room and I will stay here a little bit more so you can ask question directly to me. But if you don't have any questions, please go back to the main sessions and next lecture will start soon. Okay, thank you very much.